Alright guys, so in this video we're going over the second part of the project, which is actually deforming the bridge that we built in the last video. And it turns out deforming the bridge is like way easier than actually creating it. And so let's get into it. So first off, we should recap. What did we create in our last video? Well, first off, we created our matrix A, right, which encodes this geometric information about the bridge. We created an XC and a YC matrix, which holds the coordinates of our bridge, right, so where each fiber starts and ends in space. And then the final thing we created was a len matrix, which includes the length of all the fibers, right, which should either be 1 or the square root of 2, depending on their orientation. And so now with those matrices, we can actually do the displacement of the bridge. And I'm pretty sure most of this is included within the project documentation. I just rewrote it up here for ease of use. So the first thing you're going to do is you're going to create this stiffness matrix. And basically, you're going to be doing this line. So yeah, that's it, right? You're going to be doing your A matrix, do the transpose, blah, 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 right? And so then, once we have this stiffness matrix, we're actually going to be doing something else. We're going to be creating this displacement matrix. And so what we do is we take a stiffness, and then we do another type of division, and then we divide it by this force matrix. And I didn't actually include what the force matrix is within this video, but it's pretty simple. It's just a row vector, and then for each node that you're going to be placing one of those cars on, all you do is you place a value there, which corresponds to the weight. So this force thing isn't that hard to figure out. You guys should be able to do it. So again, we take the stiffness matrix, we divide it by our force matrix, and we get this displacement matrix. And this is actually really good. This displacement matrix actually holds the values of displacement, right? How far each node moves in space when we put these cars on top of them. But there's one kind of bad thing about this displacement matrix. All the x and y values of displacement for each of the nodes are intermingled with each other. We want to separate those out from each other. So what we do is we create these two helper matrices, which we call x and y. And so in x, we're just going to put all the x displacements for each node in there, and then for the y, we're going to place all the y values of displacements for those nodes. And so that's just for ease of use, right? Displacement has all the values intermingled. That's a little bit hard to work with, so we're just going to separate them out into the x and y. And so it turns out it's pretty easy. All we do is we look at our displacement matrix, and we take the first value, and then we skip every other one. Because remember, we're doing this idea of we associate two columns to a given node, right? So we have an x and a y column for the first node, an x and a y column for the next node. So by doing this idea, if we skip every other one, what we're doing is we're really grabbing the displacement for the A node, the displacement for the B node, and etc. And so then, if we start off with the first value and we skip every other to get the x values, well, how do we get the y values, right? We do the exact same thing, but we just start out with the second one, right? So we start out with the second value, then skip every other one. We're pulling out all the y values of the displacement. So we're taking the displacement for the A node in the y direction, the displacement for the B node in the y direction, and etc. So that's really good. We've created these x and y matrices, right, which have split up all the x and y displacements. Now it's easier for us to work with. And so the very final thing we're doing when we're modeling this deformation is, well, now we know how much each of the fibers have deformed, now we have to plot it, right? So what we do is for each fiber within our bridge, we're going to take the original x coordinates for that fiber, and we're going to add on the x values, right? To show how much it's displaced, right? So for both the left and the right sides of a given fiber, you have to take its original coordinate and then add on the value of its displacement, right? So for example, like this fiber 1, you would do is you would figure out for this side how much it deformed, which, right, it should be nothing here, right? Because that's just on the ground. It should not displace, right? And then for this side, you're going to figure out how much it's displaced, left and right. For example, again, fiber 3, right? We're going to figure out how much it's done left and right, how much up and down, how much left and right, how much up and down. So essentially what you're going to do is for every fiber, take its original coordinate, add on its displacement in order to get its new coordinates. And what you're going to do is you're going to store those new coordinate values in these two matrices dx and dy. So dx and dy are exactly the same as xc and yc structurally. It's just that now they hold those new values for where all the fibers are located in space. That way we can plot dx and dy and we can see what a deformed bridge actually looks like. So with that, I hope this video helped, and I'll talk to you guys in the next one.